And so now we're going to talk about a related idea to this idea of wanting to keep activations in a Gaussian range that we want. Right, and so this idea behind what we're going to call batch normalization is, okay, we want unit Gaussian activations. Let's just make them that way. Let's just force them to be that way. And so how does this work? So let's consider a batch of activations at some layer. Right, so now we have all of our activations coming out. If we want to make this unit Gaussian, we actually can just do this empirically, right? We can take the mean of the batch that we have so far, of the current batch, and we can just, and the variance, and we can just normalize by this, right? And so basically, instead of with weight initialization, we're setting this at the start of training so that we try and get it into a good spot that we can have, unit Gaussians at every layer, and hopefully during training this will preserve this. Now we're going to explicitly make that happen on every forward pass through the network, right? We're going to make this happen functionally, and basically by normalizing by the mean and the variance of each neuron, we look at all of the inputs coming into it and calculate the mean and the variance for that batch and normalize it by it. And the thing is that this is just a differentiable function, right? If we have our mean and our variance as constants, this is just a sequence of computational operations that we can differentiate and do backprop through this. Okay, so just as I was saying earlier, right, if we look at our input data and we think of this as we have n training examples in our current batch, and then each batch has a dimension d, we're going to compute the empirical mean and variance independently for each dimension, right? So each basically feature element. And we compute this across our batch, our current mini batch that we have, and we normalize by this. And so this is usually inserted after fully connected or convolutional layers, right? We saw that when we were multiplying by W in these layers, which we do over and over again, then we can have this bad scaling effect with each one. And so this basically is able to undo this effect, right? And since we're basically just scaling by the inputs connected to each neuron, each activation, we can apply this the same way to fully connected and convolutional layers. And the only difference is that with convolutional layers, we want to normalize not just across all the training examples and independently for each feature dimension, but we actually want to normalize jointly across both all the feature dimensions, all of the spatial locations that we have in our activation map, as well as all of the training examples. And we do this because we want to obey the convolutional property, and we want nearby locations to be normalized the same way, right? And so with a convolutional layer, we're basically going to have one mean and one standard deviation per activation map that we have, and we're going to normalize by this across all of the examples in the batch. And so this is something that you guys are going to implement in your next homework. And so all of these details are explained very clearly in this paper from 2015. And so this is a very useful technique that you want to use a lot in practice. You want to have these batch normalization layers. And so you should read this paper, go through all of the derivations, and then also go through the derivations of how to compute the gradients given this normalization operation. Okay, so one thing that I just want to point out is that it's not clear that we're doing this batch normalization right after every fully connected layer, and it's not clear that we necessarily want a unit Gaussian input to these tanh nonlinearities, because what this is doing is this is constraining you to the linear regime of this nonlinearity, and you're trying to basically say let's not have any of this saturation, but maybe a little bit of this is good, right? You want to be able to control how much saturation that you want to have. And so the way that we address this when we're doing batch normalization is that we have our normalization operation, but then after that we have this additional squashing and scaling operation. So we do our normalization, then we're going to scale by some constant gamma, and then shift by another factor of beta, right? And so what this actually does is that this allows you to be able to recover the identity function if you wanted to. So if the network wanted to, it could learn your scaling factor gamma to be just your variance. It could learn your beta to be your mean. And in this case, you can recover the identity mapping. It's as if you didn't have batch normalization. And so now you have the flexibility of doing kind of everything in between and making the network learning how to make your TANH more or less saturated and how much to do so in order to have to have good training. Okay, so just to sort of summarize the batch normalization idea, right? So given our inputs, we're going to compute our mini batch mean. So we do this for every mini batch that's coming in. We compute our variance. We normalize by this median variance, and we have this additional scaling and shifting factor. And so this improves gradient flow through the network. It's also more robust as a result. It works for more range of learning rates and different kinds of initialization. So people have seen that once you've put batch normalization in, it's just easier to train, and so that's why you should do this. And then also one thing that I just want to point out is that you can also think of this as, in a way, also doing some regularization, right? And so because now at the output of each layer, each of these activations, each of these outputs is an output of both your input X as well as the other examples in the batch that it happens to be sampled with, right? Because you're going to normalize each input data by the empirical mean over that batch. So because of that, it's no longer producing deterministic values for a given training example, and it's tying all of these inputs in a batch together. And so this basically, because it's no longer deterministic, kind of jitters your representation of X a little bit and, in a sense, gives some sort of regularization effect. Yeah, so the question is, why do we want to learn this gamma and beta to be able to learn the identity function back? And the reason is because you want to give it the flexibility, right? So what batch normalization is doing is it's forcing our data to become this unit Gaussian, our inputs to be this unit Gaussian. But even though in general this is a good idea, it's not always that this is exactly the best thing to do, right? And we saw in particular for something like a TANH, you might want to control some degree of saturation that you have. And so what this does is it gives you the flexibility of doing this exact like unit Gaussian normalization if it wants to, but also learning that maybe in this particular part of the network, maybe that's not the best thing to do. Maybe we want something still in this general idea, but slightly different, right? Slightly scaled or shifted. And so these parameters just give it that extra flexibility to learn that if it wants to. And then if the best thing to do is just batch normalization, then it'll learn the right parameters for that. So basically each neuron output, right? So we have output of a fully connected layer. We have W times X, and so we have the values of each of these outputs, and then we're going to apply batch normalization separately to each of these neurons. Yeah, so the question is that for things like reinforcement learning, you might have a really small batch size. How do you deal with this? So in practice, I guess batch normalization has been used a lot for standard convolutional neural networks, and there's actually papers on how do we want to do normalization for different kinds of recurrent networks, or some of these networks that might also be in reinforcement learning. And so there's different considerations that you might want to think of there, and this is still an active area of research. There's papers on this, and we might also talk about some of this more later. But for a typical convolutional neural network, this generally works fine. And then if you have a smaller batch size, maybe this becomes a little bit less accurate, but you still get kind of the same effect. And it's possible also that you could design your mean and variance to be computed maybe over more examples, right? And I think in practice, usually it's just okay, so you don't see this too much, but this is something that maybe could help if that was a problem. Yeah. The question is, if we force the inputs to be Gaussian, do we lose the structure, right? So no, in a sense that you can think of, like, if you had all your features distributed as a Gaussian, for example, even if you were just doing data pre-processing, this Gaussian is not losing you any structure, right? It's just shifting and scaling your data into a regime that works well for the operations that you're going to perform on it. In convolutional layers, you do have some structure that you want to preserve spatially, right? You want, like, if you look at your activation maps, you want them to relatively all make sense to each other. So in this case, you do want to take that into consideration. And so now we're going to normalize, find one mean for the entire activation map. So we only find the empirical mean and variance over training examples. And so that's something that you'll be doing in your homework, and also it's explained in the paper as well, so you should refer to that. So the question is, are we normalizing the weights so that they become Gaussian? So if I understand your question correctly, then the answer is we're normalizing the inputs to each layer. So we're not changing the weights in this. Yeah, so the question is, once we subtract by the mean and divide by the standard deviation, does this become Gaussian? And the answer is yes. So if you think about the operations that are happening, basically you're shifting by the mean, right? And so this shifts it to be zero-centered, and then you're scaling by the standard deviation. This now transforms this into a unit Gaussian. And so if you want to look more into that, I think you can look at, there's a lot of machine learning explanations that go into exactly what this, visualizing what this operation is doing. But yeah, this basically takes your data and turns it into a Gaussian distribution. So the question is, if we're going to be doing this shift in scale and learning these, is the batch normalization redundant because you could recover the identity mapping? So in the case that the network learns that identity mapping is always the best and it learns these parameters, then yeah, there would be kind of no point for batch normalization. But in practice, this doesn't happen. So in practice, we will learn this gamma and beta that's not the same as the identity mapping. So it will shift and scale by some amount, but not the amount that's going to give you an identity mapping. And so what you get is you still get this batch normalization effect, right? So having this identity mapping there, I'm only putting this here to say that in the extreme, it could learn the identity mapping, but in practice, it doesn't. Yeah, sorry. So I was not clear about this, but yeah, I think this is related to the other question earlier. So when we're doing this, we're actually getting zero mean and unit Gaussian, which puts this into a nice shape, but it doesn't have to actually be a Gaussian. So yeah, I mean, ideally, if we're looking at like inputs coming in as sort of approximately Gaussian, we would like it to have this kind of effect, but yeah, in practice, it doesn't have to be. Okay, so the last thing I just want to mention about this is that, so at test time, the batch normalization layer, we now take the empirical mean and variance from the training data. So we don't recompute this as test time. We just estimate this at training time, for example, using running averages, and then we're going to use this as at test time. So we're just going to scale by that. Okay, so now I'm going to move on to babysitting the learning process, right? So now we've defined our network architecture, and we'll talk about how do we monitor training, and how do we adjust hyperparameters as we go to get good learning results. So as always, the first step we want to do is we want to pre-process the data, right? So we want to zero mean the data, as we talked about earlier. Then we want to choose the architecture, and so here we are starting with one hidden layer of 50 neurons, for example, but we can pick any architecture that we want to start with. And then the first thing that we want to do is we initialize our network, we do a forward pass through it, right, and we want to make sure that our loss is reasonable. So we talked about this several lectures ago, where we have let's say we have a softmax classifier that we have here. We know what our loss should be when our weights are small and we have generally a diffuse distribution. Then we want it to be, the softmax classifier loss is going to be your negative log likelihood, which if we have 10 classes, it'll be something like negative log of 1 over 10, which here is around 2.3. And so we want to make sure that our loss is what we expect it to be, right? So this is a good sanity check that we want to always do. So now once we've seen that our original loss is good, now we want to, so first we want to do this having zero regularization, right? So when we disable the regularization, now our only loss term is this data loss, which is going to give 2.3 here. And so here, now we want to crank up the regularization. And when we do that, we want to see that our loss goes up, right? Because we've added this additional regularization term. So this is a good next step that you can do for your sanity check. And then now we can start training. So now if we start trying to train, what we do is, a good way to do this is to start off with a very small amount of data, right? Because if you have just a very small training set, you should be able to overfit this very well and get very good training loss on here. And so in this case, we want to turn off our regularization again and just see if we can make the loss go down to 0. And so we can see how our loss is changing as we have all of these epochs. We compute our loss at each epoch, and we want to see this go all the way down to 0, right? And here we can see that also our training accuracy is going all the way up to 1, and this makes sense, right? If you have a very small number of data, you should be able to overfit this perfectly. Okay, so now once you've done that, these are all sanity checks. Now you can start really trying to train. So now you can take your full training data and now start with a small amount of regularization, right? And let's first figure out what's a good learning rate. So learning rate is one of the most important hyperparameters, and it's something that you want to adjust first. So you want to try some value of learning rate. And here I've tried 1e negative 6, and you can see that the loss is barely changing, right? And so the reason this is barely changing is usually because your learning rate is too small, right? So when it's too small, your gradient updates are not big enough, and your cost is basically about the same. Okay, so one thing that I want to point out here is that we can notice that even though our loss was barely changing, the training and the validation accuracy jumped up to 20% very quickly. And so does anyone have any idea for why this might be the case? Why? So remember, we have a softmax function, and our loss didn't really change, but our accuracy improved a lot. Okay, so the reason for this is that here the probabilities are still pretty diffuse, right? So our loss term is still pretty similar, but when we shift all of these probabilities slightly in the right direction, because we're learning, right? Our weights are changing in the right direction. Now the accuracy all of a sudden can jump because we're taking the maximum correct value, and so we're going to get a big jump in accuracy even though our loss is still relatively diffuse. Okay, so now if we try another learning rate, now here I'm jumping in the other extreme, picking a very big learning rate, 1e negative 6. What's happening is that our cost is now giving us nans. And when you have nans, what this usually means is that basically your cost exploded. And so the reason for that is typically that your learning rate was too high. So then you can adjust your learning rate down again. Here I can see that for trying 3e to the negative 3, the cost is still exploding. So usually the rough range for learning rates that we want to look at is between 1e negative 3 and 1e negative 5. And this is the rough range that we want to be cross-validating in between. So you want to try out values in this range, and depending on whether your loss is too slow or too small or whether it's too large, adjust it based on this.
이번 시간에는 배치 노멀라이제이션에 대해서 알아보도록 하겠습니다. 배치 노멀라이제이션의 기본 아이디어는 액티베이션이 유닛 가우시안 형태를 띠도록 하는 것입니다. 첫 번째 단계로 각각의 디멘전에 대해서 민과 베리언스를 계산하도록 합니다. 두 번째 단계에서는 이를 이용해서 인풋 값을 노멀라이즈 합니다. 배치 노멀라이제이션은 대개 fully connected나 convolution layer 뒤에 배치하고 tangent hyperbolic과 같은 non-linear layer 앞에 배치합니다. 여기서 우리는 non-linear한 레이어의 인풋에 유닛 가우시안이 반드시 필요한가에 대해서 문제를 제기할 수 있습니다. 이를 보완하기 위해서 input x를 normalize해서 x hat을 구한 뒤 이에 감마를 곱하고 베타를 더해서 y 값을 얻도록 합니다. 이때 감마와 베타는 학습할 수 있는 파라미터들로서 감마가 스탠다드 데비에이션이고 베타가 평균값일 때 아이덴티티 매핑을 리커버할 수 있습니다. 배치 노멀라이제이션을 정리하면 다음과 같습니다. 인풋은 미니 배치로서 x1부터 xm까지의 값을 갖습니다. 학습되어야 되는 파라미터는 감마와 베타입니다. 아웃풋 yi는 인풋 xi에 배치 노멀라이제이션을 적용한 것입니다. 미니 배치 미는 뮤 b로 정의하고 미니 배치 베리언스는 시그마 b 자승으로 정의합니다. 노멀라이즈는 xi hat으로 표기하고 스케일 앤 쉬프트는 yi로 표기합니다. 이러한 배치 노멀라이제이션으로 네트워크를 통한 그레디언트 플로우를 계산합니다. 더 높은 러닝 레이트를 얻을 수 있습니다. 이니셜라이제이션에 대한 강한 의존도를 줄일 수 있습니다. 레귤러라이제이션의 하나의 형태로 동작합니다. 주목할 점은 배치놈 레이어가 테스트 타임과 트레이닝 타임에 다르게 동작한다는 것입니다. 민과 스탠다드 데비에이션은 테스트 타임 동안에는 계산되지 않습니다. 대신에 트레이닝 타임 때 사용된 값들이 사용됩니다. 다음은 러닝 프로세서를 베이비시팅, 돌보고 관리하는 것에 대해서 알아보겠습니다. 이는 특히 좋은 결과를 얻기 위해서 하이퍼 파라미터를 조절하는 것과 관련이 있습니다. 러닝 프로세스의 첫 단계로 우리는 데이터를 프리 프로세스에 썼습니다. 데이터를 제로 센터하고 노멀라이즈 했습니다. 다음 단계로 아키텍처를 선택하는데 여기서는 50개의 뉴런을 가진 하나의 히든 레이어의 사례로 시작하겠습니다. 인풋 레이어에는 C410 벤치마크 이미지에서 3072개의 숫자가 주어집니다. 아웃풋 레이어에는 10개의 아웃풋 뉴런이 있는데 하나의 뉴런이 하나의 클래스에 대응합니다. 코딩은 제공되는 API를 활용하면 되기 때문에 매우 간단합니다. 그러나 로스 값이 합리적인지를 체크하는 것은 중요합니다. 위에는 2레이어 모델을 이니셜라이제이션하는 함수가 있습니다. 아래에는 이 함수를 호출해서 모델을 만들고 트레이닝을 통해서 로스와 그레디언트를 계산하는 것이 나와 있습니다. 이때 로스 값을 프린트해서 값이 합리적인지를 더블 체크해 보도록 합니다. 어떤 로스 값이 합리적인지는 아키텍처마다 다릅니다. 그러나 기본적으로 로스 값이 너무 큰 경우 파라미터들이 세츄레이션 될 수 있고 너무 작은 경우 파라미터의 변화가 없을 수 있습니다. 레귤러라이제이션 값을 조정해서 로스 값에 변화를 줄 수도 있습니다. 이제 트레이닝을 시작합니다. 위의 코드에서 처음에 C410 벤치마크에서 20개 example을 가져옵니다. 레귤러라이제이션을 턴오프합니다. 간단한 바닐라 SGD 알고리즘을 사용합니다. 여러 에포크를 수행하면서 트레이닝 로스는 점점 작아지고 트레이닝 애큐러시는 1에 근접하는 것을 볼 수 있습니다. 여기서 에포크는 모든 데이터셋이 뉴럴 네트워크 전체를 한 번에 학습을 수행하는 것입니다. 배치 사이즈 곱하기 이터레이션으로 표현됩니다. 이번에는 레귤러라이제이션을 조금씩 증가시키면서 로스가 감소하는 러닝 레이트를 찾도록 합니다. 이 경우에는 러닝 레이트를 10의 마이너스 6승으로 하였는데 러닝 레이트가 너무 작아서 로스가 거의 변하지 않는 것을 볼 수 있습니다. 이번에는 반대로 러닝 레이트를 100만으로 아주 크게 증가시켰습니다. 이 경우에 코스트가 낸이 되는데 러닝 레이트가 너무 높을 경우에 발생합니다. 이번에는 3 곱하기 10의 마이너스 3승을 시도해 보았는데 아직도 너무 값이 높습니다. 몇 번의 시행착오를 통해서 러닝 레이트가 10의 마이너스 3승에서 10의 마이너스 5승 사이가 적합한 것으로 밝혀졌습니다. 이러한 하이퍼 파라미터 값들은 여러분의 데이터와 아키텍처에 따라서 달라질 수 있습니다.